Thank you very much for inviting me. So I'm very happy to be here at this inaugural conference. So what I'll talk about today is joint work with Radu Laza and Claire Lozano. So let me start by introducing what the intermediate Jacobian is of a cubic threefold. So if Y in P4 is a smooth cubic threefold, then, well, it's easy to see that H3 of Y splits into these two parts, which are both five-dimensional. So we can define the intermediate Jacobian of Y as H1 of omega 2 of Y dual modulo the third integral homology. So this governs one cycles on Y. And in fact, there's an Abel-Jacobi map, so, which goes from Chow2 of Y, homologous to, could I mention two cycles that are homologous to 0? If Z is such a cycle, then we can write it as the boundary of a 3-cycle. And so what we map it to is the integral over Y. So we're in the right part. So this is a function on this space. We're in the right part of the Hodge filtration so that this integral is well defined. Though, of course, here we have some, we could choose up to a co-boundary. So this is why we only land into, we have to mod out by the periods. But anyways, by the fact that the H3 has that form, this is principally polarized. So it's a principally polarized Debian variety of dimension 5. So what we'll do is if X is a cubic fourfold, then what we can do is can do this construction relatively. So if U is parameterized as a hyperplane sections of X, then we can consider, so P5 is a hyperplane sections. These are the smooth hyperplane sections, and we have the universal family, and we can consider the universal intermediate Jacobian here over P5. So this is a U. So the aim of the talk is to compactify this into a holomorphic symplectic manifold or a hyperkähler manifold. So before I talk about this part of the story, let me first remind you how Clemens and Griffiths use this to show that the smooth cubic threefolds are not rational. And the reason why I want to introduce this is because their story relates the intermediate Jacobian of a cubic threefold with a certain prim variety, and we'll use the prim varieties to find this compactification. So, so Clemens and Griffiths. So we can choose a line inside Y. Well, it's rationally connected. In particular, we can find one line, and we can project onto P2 from, this is contained in P4, so we can project onto a P2. So blowing up this line, we have a regular map, which in fact is a conic bundle. Conic bundle. And well, simply because if I take a plane, any plane that contains the line, it will intersect Y in a degree 3 plane curve, and so generically it's going to be the line plus a conic. But there's a locus here, which I'll denote C, and it depends on the line L, where in fact the conic will break into the union of two lines. So in fact, so a point here corresponds to the choice of the two lines. So there's a natural double cover here, 2 to 1. I'll denote it by C twiddle L. That in fact, so this is the curves of lines in Y that meet L. And so the double cover to a plane like this just associates the two distinct lines. And so I'll denote by I the involution that acts on here. So this is, so I have the freedom to choose the line in this construction. In particular, Clemens and Griffiths show that there is something that you can call a good line. And for good lines, what happens is that it never happens that one of the P2s that I consider here breaks into either twice the line plus another line, or the line and then twice another line. And this guarantees two things, that this curve here is smooth, and that the map is étale. Also, so smooth, this is a plane quintic, so at genus 6. Because this parameterizes lines on Y, I can consider the Abel-Jacobi map for this curve. So it has values into this guy. So if I have a point here, well, it corresponds to a line Lx. And so I'll just map this to the Abel-Jacobi map of the line that I fixed minus this line. These are homologous, so this is a well-defined map. The point is that this induces a map from pick 0 of C twiddle into the intermediate Jacobian, just by general principle. And the point is that the involution here, of course, interchanges this line with this line. So in fact, so this is a line L. The line, the union of L plus L x plus L iota x, this is just rationally equivalent to the hyperplane section squared. And so in particular, this is constant. The reason why I'm saying is that this map factors, so the kernel of this map is exactly the invariant part of the Jacobian of this curve. And in particular, it factors through the anti-invariant part, which is the prim variety of C twiddle over C L. And this, I can consider it as sitting inside pick naught of C twiddle L as the anti-invariant part. So either the image of 1 minus iota, or also as one component of the fixed locus of the anti-invariant part. So, and the point, what I wanted to say here is that this map factors like this, and Mumford showed that this, in fact, is an isomorphism. So this is why, how we will compactify this thing here by taking prim varieties of singular double covers and adding them here. So the starting point of this story is theorem of Donaghy and Markman. In the 90s, I think 94, something like that. And the theorem is that, so consider x cubic fourfold, and so let Ju over U be the relative intermediate Jacobian of the family of smooth hyperplane section of a fixed cubic fourfold. So the theorem of Donaghy and Markman is that there exists a holomorphic symplectic form, which I'll denote by sigma U, on the total space of this family. And with respect to which this map is Lagrangian. This map pi is Lagrangian. And I guess I also proved that it's closed. So they have a general machinery that, given a family of principally polarized abelian varieties, they have a necessary and sufficient condition for the existence of a holomorphic symplectic form in this case, but it only works for the smooth things. So what they ask is, question is, can you compactify? Does there exist a compactification, say J bar, maybe over P5, such that this sigma u extends to a holomorphic symplectic form? So here I should have said not only a holomorphic 2 form, but if I didn't say it, symplectic, so non-degenerate, to a holomorphic symplectic form on this J bar. So a compactification may be smooth, so J bar is smooth projective, such that the holomorphic 2 form that is only defined in an open subset extends, and not only to a holomorphic 2 form, but also to a symplectic 2 form. Yes, yeah, thank you. To a closed. Well, I guess if it's projective. Oh, sorry. This, yes, sorry. Here we don't need it because if it's projective, it's automatic from. Okay. All right. So then I guess it was formulated as a conjecture a bit later by I think I should. So the conjecture is by Markushevich, Tikhonov, and Kuznetsov in a sequence of different papers. And so the conjecture is that, yes, there exists a J bar smooth projective compactification that is a hyperkähler manifold. So I'll just use interchangeably hyperkähler and for irreducible holomorphic symplectic manifold. So I mean smooth, in our case everything will be projective, but with a holomorphic symplectic form, simply connected, and the symplectic form is unique up to scalar. So this is the thing, but also that this J bar is deformation equivalent to O'Grady 10. So maybe I should remind you what O'Grady 10. So this is one of the exceptional examples of hyperkähler manifolds. So if S is a K3, and I can consider the ideal sheaf of 2 points on the K3, and I can consider its Mukai vector. I call it V0. So I'm just fixing the Chern classes. So if I consider the moduli space of sheaves with Mukai vector equals to 2V0, so it's a theorem of O'Grady that there exist M twiddle to M F a symplectic resolution. So counting dimension of this is a 10-dimensional moduli space. So O'Grady also has a similar construction where you start instead with an abelian surface, and it's 6-dimensional. So this is why I call it O'Grady 10. There's O'Grady 10 or O'Grady 6. These are the two exceptional examples. So, so yeah, the conjecture is that, yes, there exists a compactification, and that the compactification is deformation equivalent to O'Grady 10. So I should say that the story of hyperkähler manifolds in cubic fourfolds is very long, and before I talk about our result, I'll just say a few words about this. So it's so I guess it starts with Bavil-Donaghy, cubic fourfolds, and hyperkähler manifolds. Here I will assume hyperkähler manifolds have dimension greater or equal to 4. So I'm not talking about cubic fourfolds and K3 surfaces, which is another very interesting story. So so X, as before, a smooth cubic fourfold. Then, so H4 of X has following Hodge decomposition, H31 plus H22 plus H13. I guess that using the Jacobian ideals that Daniel was mentioning yesterday, you can show that this is one-dimensional. So, so H1 omega 3 of X is one-dimensional, and it is generated by a class that I'll call eta. So, so when you the examples of hyperkähler manifolds that we know all come from either a K3 surface or an abelian surface, and well, apart from the ones that I'm going to describe in a second, but the ones we started with, so to say. And the holomorphic symplectic form always comes from the holomorphic 2 form on the K3. And the analog of that thing there will be played by this form eta in the way that I will show in a second. So, yeah, okay. Well, I mean, this is 121, 1, but I guess I don't really need this. Anyways, so the story starts with Bavil and Donaghy. And Donaghy is a result that has been mentioned in various talks so far, so I'll be very quick. So if I let f of x be the Fano of lines, so in X, F, L, a line. So this is, so their theorem is that this is a hyperkähler fourfold. Hyperkähler fourfold, and it's deformation of Hilb 2 of a K3. And they prove it by going to the Pfaffian locus, and there it's a pretty explicit construction which uses the description of the Pfaffian description. And, what I want to mention now is that if I denote by gamma the universal line, so I guess in f of x cross x, so this has the two projections on this and on this. And the point is that, can I write here? Okay, I'll go up there. So the point is that I can use this gamma, this correspondence, to get a map from H4 of x into H2 of f of x. And this is a Hodge morphism of Hodge structures B degree -1, -1. So in particular, eta that was a 3-1 form goes into something I'll call sigma that is a 2-0 form. And this 2-0 form is exactly the symplectic form that comes here. So the reason why I say is that how one of the results that we have, or maybe, yeah, is that well, we find another way of defining the Donaghy-Markman holomorphic symplectic form, and it uses a correspondence like this. So this is why I mentioned this. So other examples are the Lan, Sawyer, and Stratton eightfold, which is essentially a moduli space of twisted cubics. So if I consider the moduli space of twisted cubics on X, then the universal family of cubics gives, as in this case, a holomorphic 2 form here, but except that it's not symplectic like in this case, but you have to contract. So if you contract first a P2 bundle and then you blow down a divisor, you get this F3 of X, which is hyperkähler. And by result of Addington and Lan, This is a deformation of Hib4 of a K3. So anyways, this thing about considering moduli space of rational curves of certain degrees on a cubic fourfold was started by de Jong and Starr. And so this is sort of going along these lines. And the point is that the fact that you define it as a correspondence tells you that this holomorphic 2 form actually extends on any smooth birational model of the moduli space you're considering. So this is why the answer to the question, as I'll say in a second, does the homomorphic symplectic form extend to a homomorphic form, actually comes almost for free. I should say that, so we had an email from Kolar that told us that using minimal model program, you can actually find compactification with, I think, canonical singularities. But the point is that you don't know, actually, if these canonical singularities actually admit a symplectic resolution or not. So our method is a little more explicit, so it allows us to actually show that the compactification that we get is smooth. Okay. And there's another thing I wanted to say. I'm running a little out of time, but I just will mention it briefly. So, because it ties to the talk of Baville and also to the talk of Huybrechts. And there's other connection of cubic fourfolds and hyperkähler manifolds, which I think was started by Markuszewicz and Tikhomirov. And also I should mention maybe Duell's name. And so there's certain moduli space of, so maybe I'll just say very briefly. So back to Y, take the moduli space My of semi-stable sheaves of the following Chern classes. So rank 2, C1 equals to 0, and C2 equals to 2. Then the Chern class map has values into sort of the degree 2. So this is a twist of the other thing. But what I wanted to say here is that there's an open subset here, which corresponds to the Ulrichs bundle that appeared in Baville's talk. And the point is that you can do this relatively, say on the smooth locus. And so you get both a map to U and to a map to this JU. And this, of course, so this is a blow-up of the Fano here, the conics, in fact. And this also is a blow-up. And the connection with Daniel's talk is that so you can view this as moduli spaces. So this is a twist of ours. It's a degree 2 case. It's not, ours will have a section. This is the torsor over it. So the connection with Daniel's talk is that this can be seen as a moduli space of objects on X. And if you look at this U thing, this relative locus of the Ulrich bundles, that's exactly where, so the moduli space of objects on X has a holomorphic 2 form, which was defined by Markuszewicz and Kuznetsov using a degeneration, a sort of generalization of the Mukai pairing. But the point is that this locus is exactly where this holomorphic 2 form is non-degenerate. And it's actually the locus of sheaves that were in that AX category that Daniel had. Oh, sorry. Okay, anyways, that was a side remark because it's not really something that we use here, but it was just to show how, in fact, the connections with cubic fourfolds is very rich. And in fact, we're not going to compactify this, even though I think we're optimistic that that's something that can be done. We just compactify the one that admits a section. So let me just, it's clear what the theorem is, but let me just write it down. And so the theorem is just that, yes, there exists a J and a map to P5, compactifying this JU. This map I'll denote by pi. And so J has, so maybe I should say it in this order. Pi is flat, equidimensional, and J is holomorphic as a hyperkähler manifold, and its deformation to already 10. The reason is I say it in this order. For the people that know Lagrangian fibration, it's clear that once I have something like this, and this is a hyperkähler, the map is going to be equidimensional. But in fact, how we prove it is we first compactify to a flat map, and then get the result. So I will sketch the proof of the theorem. First, I should say some corollary, well, I guess one corollary, which is the following. So this is, so the first example of a hyperkähler manifold that is fibered in principally polarized abelian varieties that are not Jacobians. As I said earlier, the intermediate Jacobians are prim varieties, and Mumford has shown that in the case that we are in, that prim variety is not the Jacobian of a curve or a product of Jacobians of curves. And so all the other examples of hyperkähler manifolds that were fibered in things that were principally polarized were essentially Baville-Mukai system. So I guess that there had been examples of things fibered in prim varieties, but either they were singular or they actually were prim varieties that were secretly Jacobian of curves. So I guess that, yeah. They're all, yes, that's right, yes. So, yeah, but I think it's, under some other assumption, I think Justin Sewan has a result that says that without asking for it to be already a deformation of the Hilb of a K3, with some mild assumptions on the family of curves, he also proves that. So he proved that, so take a family of curves, I think like integral curves and maybe locally planar singularities or something. Suppose that the relative compactified Jacobian is smooth and has a holomorphic symplectic form, then the family of curves was a linear system of curves on a K3 surface. So, I mean, what I'm not saying is that if I have a curve on a K3 and I consider the linear system, say this is genus G, then I can consider the relative compactified Jacobian of this, and that's a hyperkähler. And so basically, what this result, as I mentioned, saying, with some assumptions that maybe I'm forgetting some numerical things, but if you have a family of curves of genus G over a PG, and the relative compactified Jacobian is smooth hyperkähler, then they're on a K3 surface. Okay. So I guess I'll spend the rest of the talk.
You didn't write it, but the form is the same as the...
Oh, yes, thank you, yes. And the symplectic form extends the Nagy-Markman sigma u. Thank you. Okay, so there are two ingredients of the proof. So one is the cycle-theoretic symplectic form along the lines of what I was describing earlier of this, the Fano lines or the moduli space of Quistit qubits. And the other thing is that degeneration of prim varieties and so I guess the sort of generalizations of Clements and Griffiths on one side because you want to do the same game, but allowing the hyperplane section to acquire singularities, and then a smoothness criterion. Smoothness criterion, which is essentially a prim version of the Fontecchi-Gucci-von Straten smoothness criterion for Jacobian of curves. So let me start with the following proposition. So first of all, I should say that there exists a partial compactification so if so U was a set of the smooth one, and then U1 in the P5 are the cubic threefolds with at worst an A1 singularity. So there exists a partial compactification U1 over this, which also was considered, in fact, by Donaghy and Markman. So this is just the sort of rank 1 degenerations of a family of abelian varieties. So this is just something sort of, I guess, canonical in some sense. So the proposition is this. So for any J bar smooth projective compactification of our JU, then there exists a sigma bar extending this sigma U in not holomorphic symplectic, a holomorphic 2 form. So H2 of J bar. So this is the first statement. And the second statement is that if J bar is actually compactification of this guy, then this sigma bar is non-degenerate over this JU1. And so this, what I'm saying is that if this is non-degenerate over U1. Well, not yet. Yeah, but this is So that's exactly what I was about to say. So now this is just a random compactification I could have blown up, and so the corollary of this is that if J bar is equidimensional over P5, if it has a map to 5 and it's equidimensional, then because the complement has codimension greater or equal to 2, if it's equidimensional, then this also is complement of codimension 2, and so this would imply that J bar is hyperkähler. So the first thing just tells you that the symplectic form extends on any smooth projective compactification to something possibly degenerate. The second thing tells you where it's non-degenerate. So if, this is flat, so that this complement has codimension 2, then there's no space for being degenerate. So this is what we want.
You know it's impassive holomorphic symplectic. How do you know it's right away it's simply connected?
Well, you can't. So this thing contains, and so the compactification that we find contains a P1 bundle over the Lend-Sorger thing, and so this is how you prove that the symplectic form is unique. But in fact, once you know that it's birational to O'Grady 10, then it's automatically simply connected, and H20 is 1. So yeah. So I'll just sort of give a brief sketch of this, and then I will talk about the generation of prim varieties. So the examples that we saw earlier, the 3-1 form on X gave a holomorphic 2 form on the moduli space of things that we are parameterizing by this correspondence. So we kind of want to do the same thing. And here, as I said earlier, the intermediate Jacobians somehow parameterize 1 cycles. And in fact, it turns out that, so if t is in U, so I'm like fixing a yt, I can consider a codimension 2 cycle in the product, I first have to set jt cross yt. Maybe I need with rational coefficient such that this, this gives an isomorphism between h1, h3 of yt with h1 of jt. So this is, follows from the fact that y is Fano. In particular, it's a unirule threefold. And so there's a surjectivity of the Abel-Jacobi map, which in fact gives this cycle. So what you do is you want to spread this out. So over the smooth locus, you consider a cycle here in the fiber product. And in fact, you can map this into, this has the evaluation map into X. So I just consider this. What I'm doing is just I'm trying to do this thing relatively, and I get a cycle here. This map, and I get a cycle here. And the point is that once I have a cycle, I can just close this thing here, this ZU, inside any compactification, smooth projective of this, and just do the same game as I was doing earlier. This gives a correspondence from the cohomology of this to the cohomology of this. And so this is a cycle, a codimension 2 cycle, maybe with rational coefficients, that induces the sort of isomorphism between H3 of YT and H1 of JT. So remember, JT was the H1 omega 2 YT dual over H3 of YTZ, right? And so, yeah, and so the H1 of this guy is the H3 of that guy. And the claim is that there exists a cycle that defines that isomorphism. And then what you do, you spread it out, and then because it's defined in terms of cycle, you can just close it, and you get this, let me just call it Z, and from H4 of X into H2 of any smooth projective thing. And as before, you get the eta form here maps to something that I'll call sigma. So in fact, you see that as soon as this thing is non-zero, then the transcendental cohomology of this embeds into that. In particular, you see that the B2 of compactification is bounded by below by, I think it's 24. So make...
You have not yet explained how the J varies. I'm sorry.
No, this is for any. So I take any smooth projective compactification, and I have a holomorphic symplectic form there. So now what you do is that you have to pick one such that the map to P5 is flat. Well, that contains that JU1 that I, does that make sense? And this is done by using degeneration of prims. So this is what I'm going to talk about next. I guess I won't, yeah. It's nice to see how it's, you use a Lagrangian fibration. I'll just say in words. Basically, I think it's a very nice thing. So given a Lagrangian fibration, so this holomorphic 2 form in particular is such that the fibers of this map are isotropic. And so this gives you a map between the vertical tangent space and the cotangent space of the base. And so using this is why I said this here. Using this, you can see that this map is an isomorphism from the vertical to the cotangent of the base. And this is how you prove that it's non-degenerate. I mean, I'm just kind of hand-waving, but anyways, I can say more maybe at the end if there's time. So, so I guess well, maybe actually I do have time to say it. Let me just say it. So this, I said the fibers are, so let me pick a T. So I'm just fixing one smooth hyperplane, and I have this JT here, a fiber. So the point is that this is a holomorphic 2 form, so contraction gives me a map from the tangent space of JU to the cotangent space of JU. This is just because it's a holomorphic 2 form. So let me restrict to a fiber. And let me consider the tangent space of the tangent space sequence here. So the tangent space of the fiber goes to this, and then I have the tangent space, the pullback of the tangent space of U at the point T. And here I have the cotangent bundle sequence of omega j of the fiber. I'm on the smooth point, so everything is. And here I have the pullback of the cotangent bundle of the base. So the fact that the 3-1 form on X restricts to 0 on the hyperplane section tells me that the composition of this map is 0. In particular, I have a map here and a map here. So this is just the sort of cup product with sigma. So to prove that the symplectic form is non-degenerate is equivalent to showing that this map is an isomorphism. And to show that this map is an isomorphism, it's enough to show that these two things are isomorphism, but in fact these are dual to each other. So we'll just look at this thing here. So these are both trivial bundles because this is a pullback and this is just the cotangent bundle of an abelian variety. So we can just prove it at a point. So what is this? The tangent, so U was inside P5, which is just P of H0 of, so OX of 1. So the tangent space there is the OT, YOT, O1. Which is the tangent space to projective space in that point. Whereas this is H0 of JT, omega 1 of JT. And so we have this map here, which is induced by sigma. Let me call it sigma t. And we have this map. We want to show it's an isomorphism. So, well, this, using that cycle ZT that I wrote on the board, this is just the H1 omega 2 YT. This is just that ZT isomorphism that I had there. And basically, so what you see is that this map is the cup product with a form that I'll denote by eta t, which lies in H1 of YT omega 2 yt of minus 1. Okay, let me say where this comes from. But if I prove that this commutes, then because this is an isomorphism, and this is actually cup product with an extension class which is not trivial. In fact, this map is also an isomorphism. And where does this come from? So so the omega 3 of x restricted to yt goes to omega 3 of yt, and the kernel is omega 2 yt minus 1. So H1, the form eta here restricts to 0, so it comes, in fact, from a unique form that is just this. So just by using how this form has been constructed, you can see that you can see how it acts on these fibers, and you can show that, in fact, this map is an isomorphism. You have to prove that cup product is an isomorphism, but it's okay. Anyways, prim varieties. So so we have U and we have the P5, and we have this JU, and we want to get something here. So what you can do is sort of you can do the Clemens and Griffiths thing for Y possibly singular. So I guess and you do exactly the same thing, and you get a double cover of curves. Like before, you just project from a plane, except that in this case, these curves possibly acquire singularity. So I guess that this point of view of using the Clemens-Griffiths construction for possibly singular cubic threefolds, I guess, was started by Casalina, Martin, and Laza, and maybe Bovell too. So their aim was to extend the period map from the moduli space of cubic threefolds, maybe GAT compactification to some compactification of A5. So maybe some partial compactification here, some decoration here. And so the point of view here is slightly different because we want to compactify over a fixed space, and we don't want to allow ourselves the liberty of possibly blowing up something here to get the map defined. So we do use some of the results here. In particular, I'm going to say it in a second. When I did the Clemens-Griffiths thing in the smooth case, one of the results was that I could choose a line such that the curve was smooth and the map was étale. And so Radu and Janos started this thing of finding lines in cubic threefolds, possibly singular cubic threefolds, that are such that the corresponding double cover of curves is sort of nice enough. And so I guess their point of view, they early needed GAT stable things, but so sort of adding a little bit, we get is that if X is general, then for any hyperplane section in X, there exists an L, what we call a very good line. And so good line means as before, so that the map is étale, C twiddle L to C is étale, and also that the singularities of CL are essentially the same the singularities of Y. And the very good here is that the C twiddle L is irreducible. So there's something slightly more because there's a versal statement, but I'm going to say that later. So, so the point is that so if I have a any plane. Yeah. So should think about now which statement is which. But one statement is that if L is not double, tells you the singularities, and the fact that L and the other curve is not double tells you that it's a tau. I think I got it right, but one is the other. And so we have a sort of different proof of the one of Radognano that uses the geometry of f of x and the fact that this is general. So the statement now that I want to do, so now I have a double cover of possibly singular curves, and so using this, I'm going to assume that, so C is a planar curve, so, and the map is étale, 2 to 1, so I assume the curves C twiddle and C locally planar, and also C twiddle irreducible. So I still have an involution here acting on the curve upstairs. It's a fixed point free involution. And I can consider the pick 0 of C twiddle. And of course, I can still act, this is a group, I can still act by iota star and by minus iota star. So I still have a fixed locus of this involution. Though, of course, if these guys are singular, this is going to be non-compact in general. So the point is that there's a sort of well-developed theory of compactified Jacobians. So I can close the Picard consider the compactified Jacobian. And so the point is that under these two conditions, I can extend this involution here. And the fact that the singularities are locally planar guarantees that any torsion-free sheaf here is reflexive. And the fact that it's irreducible tells me that I don't have to worry about multiple components, and I don't have to worry about -1 messing up the stability or the degree of the curves. So anyways, what you can do is you consider the fixed locus inside this guy, and maybe you want to consider one connected component. Turns out that irreducible and connected component, in this case, it's the same. And this is what I will denote by prim, compactified prim of C twiddle over C. So now what you want to do is you want to do this thing in families. And so if I have a family of these curves, CB over 2 to 1, with curves in these families that are locally planar irreducible, then you can define, so you can take the relative compactified Jacobian of the curve upstairs like this, just doing this, the thing I'm doing here, but moving here. And as before, I can act with this minus iota star here. So the definition is that you define the relative prim variety, relative compactified prim variety of C twiddle over C to be the fixed locus, the component of the fixed locus of minus star that contains the identity. This is the degree 0, so I have a 0 section, and I could take the fixed locus of this involution acting here that contains that. And so in particular, it has a map, say V, onto B. And the proposition is the following. So first of all, this definition commutes with base change. A priori, you could pick up different components, but in fact, you don't. And the map, so this map from the prim, let me just denote it by P bar B over B is flat. And then we have the smoothness criterion, which is the following. So let me pick element B in the base, and let me look at the fiber this of the prim variety over that thing, which by this is just the prim of the curve CB over C twiddle B over CB. And I want to check, so this of course is going to be very singular, but I'm asking whether the total space is smooth or singular along this fiber. And the condition that guarantees it is the following. So, so B is in particular a family of curves. So I can consider it as a family of deformations of the curve CB. So if this is a versatile deformation of the curve, of this curve CB, then this relative prim variety is smooth along the fiber. Yeah, so yeah, well, yeah. I mean, of all the singularities. I mean, it's actually slightly, you only need that the tangent map from the tangent space of B at little b into the deformation of the curve is transversal to the equigeneric stratum. So basically, you want to smooth out the points with liberty. So so this is a smoothness criterion. So it turns out that sort of in this proposition, what I said about the versatility, which I didn't say, but it follows from Casalaina, Martin, and Laza, is that in fact, when you consider the family of hyperplane sections of a cubic fourfold with the choice of a line, you do get this versatility statement. And so this guarantees that over the family which parametrizes cubic hyperplane sections and the choice of a line, you have this relative compactified prim variety, which is smooth.
So this construction doesn't use anywhere that the curves are plane curves, right?
The locally planar, yes. Well, for example, you use that the fibers are reducible in this construction.
You do it over the moduli space of double covers, I mean, or the Enriquez over any compactification of R6 bar. You're not using that. You're on the inverted Jacobian.
Oh no, but oh yeah, no, sure. This, yeah. You only what you do use is that locally planar and irreducible. So if you don't have this, I'm not sure what happens. But in fact, I mean, in a sort of hidden version, this appeared in a paper with Enrico and Ferretti that we were doing of the, I guess, I don't know if that's where you're thinking, the same thing where with a specific family of curves that came from Enrico's surface. There it turned out that the family was smooth, but the reason why it was smooth was actually, in fact, this criterion. And the point that that it's subtle. So you define the prim as a fixed locus. So of course, if the ambient space is smooth, then the fixed locus will be smooth. But the point is that this family here is never versal, because you never smooth. So if you have a singular curve point here, you have two singular points here. So this deformation always keeps the same singularity at these 2 points. So the relative Jacobian of this thing here is never going to be smooth. But nevertheless, when you take the fixed locus, it's actually smooth. And and the reason is that you can kind of extend the base and sort of embed this into a bigger family of curves where the compactified Jacobian is smooth and the fixed locus of these two families is the same. I guess my time is up. So I just say that this construction all depends on the choice of a line. So then you have to get rid of it. And so for this, you use a relative theta divisor, which is actually defined in this case. And so on the family of on the smooth locus, it has a nice geometric interpretation. But in fact, what you managed to show is that you can extend it to a relatively ample divisor also on the singular thing. And that allows you to get rid of the choice of the line and get something that is here. Okay, thank you.